Hello everyone. So, today in this third lecture we are going to continue our discussion on the refrigeration cycles. Over previous two lectures we have discussed primarily about the vapor compression based refrigeration cycle, where we have already seen different variations of that, particularly starting with the Carnot cycle. We have discussed about the triple S cycle, which is the most common vapor compression type cycle, and we also have discussed about its applications and the refrigerants. Now, in the last lecture, towards the end of the second lecture, we have discussed about the desirable properties of the refrigerants, and then we are supposed to discuss about the naming convention of the synthetic refrigerants that we commonly use in refrigerators or in refrigeration cycle systems, but we ran out of time. So, today I shall be starting with the naming convention of refrigerants. Now, there are several kinds of refrigerants that we commonly use in refrigeration system, depending upon the application, depending upon the prevailing pressure and temperature ranges, etc. And the most common type of refrigerant that we have is the synthetic FC based refrigerant. FC refers to fluorochloro, that is fluorine and chlorine based refrigerants. So, synthetic fluorine chlorine based refrigerants are the most common types. You probably remember that we have used the terms CFC, HCFC and HFC in the previous lecture, where CFC refers to chlorofluorocarbon, HCFC is a hydrochlorofluorocarbon and HFC is a hydrofluorocarbon. These are different kinds of FC based refrigerants, where you generally have fluorine and chlorine in the molecular structure present. Now, synthetic FC based refrigerants can be derived from different kinds of hydrocarbon groups or saturated hydrocarbon groups, but we shall be restricting our focus on the saturated hydrocarbon, that is we shall be focusing only on the alkenes which have the structure generally CN H2N plus 2. Like common example can be methane, where n equal to 1, if you put n equal to 1, then H will be having the number 4, or if we put n equal to 2, then what will be the number of hydrogen? It will be C2H6, the ethane. So, these are alkanes. So, we shall be talking about the synthetic FC based refrigerants whose structures are based upon alkanes. The idea is the carbon that is there in the alkane will remain the same, but all the hydrogen atoms or maybe some of the hydrogen atoms will be replaced by fluorine and chlorine. Then we shall be having some kind of FC based refrigerant. And for this kind of refrigerant, you will always find that the name is given with the convention R, X, Y, Z, R11, R12, R134, these are the different names that we have we keep on hearing about the refrigerants, and this is the convention R, X, Y, Z, where R refers to refrigerant and X, Y, Z refers or gives some idea about the molecular structure. Here X is the number of carbon minus 1. X refers to the number of carbon present in the molecular structure minus 1. Therefore, number of carbon is X plus 1, and what is the when we know that number of carbon is X plus 1, what will be the number of other molecules or other atoms, I should say, that excluding carbon basically. So, we know that has to be twice of the number of carbon plus 2. So, it will be 2 into x plus 1 plus 2. Now, here Y refers to the number of hydrogen remaining in this plus 1. Therefore, number of hydrogen will be equal to Y minus 1. So, X refers to the number of carbon minus 1, where Y refers to the number of hydrogen plus 1, and Z or Z, this refers to number of fluorine that is present in this. Generally, we are too much bothered about the presence of chlorine in the synthetic refrigerants, because chlorine is the one that leads to the ozone depletion potential, as we have discussed in the previous lecture. When this chlorine comes out of the molecular structure in the presence of UV rays, that generally breaks the ozone down to form oxygen, thereby depleting the ozone layer. But unfortunately, in this naming convention, chlorine does not appear directly, rather chlorine we have to calculate separately. We know the number of once we know the magnitude of x, y and z, we know the magnitudes, or sorry, we know the number of some carbon, hydrogen and fluorine present there. Then we now can write number of fluorine is equal to Z. Then what will be the number of chlorine? We know that apart from carbon the number of other atoms is 2 into x plus 1 plus 2. Out of this hydrogen is y minus 1 number and fluorine is Z number. So, from there we can easily find the number of total chlorine that is present there. Let us take some example. If we have R11, instead of writing here we have just 2 numbers present instead of 3. So, you can also write this one as R011. So, what will be the number of carbon? Here your x is equal to 0, y equal to 1, z equal to 1. Then what is the total number of carbon? Carbon is equal to x plus 1, that is equal to 1, hydrogen is equal to y minus 1, that is 0, fluorine is equal to z, that is equal to 1. Then how much will be the number of chlorine there? Number of chlorine will be equal to 2 into x plus 1 plus 2 minus y minus 1 minus z. So, from there you can calculate, or we can calculate directly, as there is just one carbon atom. So, the from the 2n plus 2 we can easily calculate total number of other atoms will be equal to 4. Out of this there is no hydrogen, there is 1 fluorine. So, there will be 3 chlorine. Then what will be the molecular structure of R11 then? So, R11 will be equivalent to Cl3F, that is trichlorofluorocarbon, or I should say trichlorofluoromethane. That is the molecular name, or that is the standard name or scientific name of this R11. Instead of R11, if we talk about R12, so we are having R12, so it is 0, 1, 2. So, x is equal to 0, y equal to 1 and z equal to 2. So, number of carbon will be x plus 1, that is 1. Let us remove all this. So, number of carbons will be x plus 1, that is 1. Number of hydrogen is y minus 1, that remains 0. Number of fluorine in this case is 2. So, how much will be the number of chlorine? Number of chlorine will be equal to 4 minus 0 minus 2, that is equal to 2. So, how to represent this one? R12, then R12 will be equal to C, Cl2F2, difluoromethane, whereas R11 is trichlorofluoromethane or trichloromonofluoromethane. R12 is difluoromethane. If we talk about something else, let us take another example of R22, another very popular refrigerant generally used for large scale commercial applications. Here again we can write 0, 2, 2. So, number x is 0, y is equal to 2 and z is equal to also 2. Now, how many number of carbons present here? 0 plus 1, that is equal to 1. So, it is also methane based, there is just one carbon. Now, there is hydrogen 2 minus 1, that is 1 hydrogen is present, and there is 1 fluorine also. Then total number of chlorine, as there is only one carbon, so total number of other atoms will be twice of that number of carbon plus 2, that is equal to 4 minus 1 hydrogen minus 2 fluorine, that will be equal to 1. So, R22 will be equal to C. Now, there is 1 hydrogen, so H, there is 1 chlorine Cl F2. So, these two are CFC, because in the molecular structure you have carbon, fluorine and chlorine, whereas this one is an HCFC, hydrochlorofluorocarbon, because hydrogen is also present there, this HCFC. We take another very common example, R134A. So, here we have, let us just write as R134. So, x equal to 1, y equal to 3, z equal to 4. So, number of chlorine in this case, or okay, first let us calculate the number of carbon. So, there is x is equal to 1, so it is 1 plus 1 equal to 2. So, there are 2 carbons, so that is actually in ethane based. previous 3 examples that we talked about, R11, R12 or R22, they are all methane based, whereas R134A, there it has 2 carbon in its molecular structure, so it is an ethane based one. Number of hydrogen 3 minus 1, that is equal to 2. Number of fluorine, it is equal to 4. Then total number of chlorine, how much it will be? So, as there are 2 carbons, so total number of other atoms will be equal to 6, minus there is 2 hydrogen, minus there is 4, that is equal to 0, that is there is no chlorine present there. So, R134A is C. Now, we have 2 carbons and there is 2 hydrogen and 4 fluorine. So, it is an ethane structure and it is you can say tetrafluoroethane, you can say the name of this one is tetrafluoroethane. Now, what is the type of this, CFC, HCFC or HFC? This is an HFC because there is no chlorine present there and therefore, its ozone depletion potential will be, it is 0, as there is no chlorine present. So, its ozone depletion potential has to be 0. So, it is an much more environment friendly one compared to the earlier 3, because earlier 3 R11, R12 or R22 all are having chlorine present there. So, they have ozone depletion potential which R134 does not have. However, global warming potential is there for all of them. So, this is the way we give the names to several common refrigerants, or I should say the synthetic fluorochloro based refrigerants. This is the naming convention that we commonly follow. Here of course, I should mention that R134A, the A refers to is an isomer, means it is also possible to have a few other molecular structure using the same combination. So, it is just one of several possibles. I would request you to calculate a few others just following the same convention, say R121 or something. You can just put some numbers and try to see what can be the corresponding molecular structure. Now, second is we have the pure fluid based inorganic refrigerants. Pure fluid based inorganic refrigerants refers to the natural refrigerants like ammonia, carbon dioxide, even water vapor, though that is not very commonly used, but they all come under this category. And here our naming convention is very straightforward. Naming convention is R7XY. The 7 is a fixed one and this XY, it refers to the molecular weight. So, it is a very simple convention. This 7 actually corresponds to this inorganic refrigerants or natural refrigerants and XY is the molecular weight. Like suppose if we take ammonia, ammonia has a molecular weight of nitrogen is 14 plus 3 into 1 for hydrogen. So, 17, then its name will be R717. If we take H2O, for H2O it is 2 into 1 for hydrogen plus 16 for water. So, it is 18. So, it will be equal to R718 for water vapor. Another very popular refrigerant nowadays for large scale application, particularly CO2. How much it will be? Now, carbon is 12 plus 2 into 16, that is 44 is the molecular weight for carbon dioxide. So, it will be R744. This way you can easily put something like sulfur dioxide or any other chemicals, you can just put this XY or replace this XY by the molecular weight and you can get their name. Third is the pure fluids. Pure fluids generally refers to hydrocarbons. Previous one was a pure fluid based on inorganic refrigerants, here whereas here we are talking about pure fluids based on the organic refrigerants like the hydrocarbons. Now, here the naming convention is very similar to the synthetic FC based refrigerants, that is we shall be following our XYZ, and here the XYZ convention is very similar to the number 1. Like let us take the example of say R290. So, in this case we have x equal to 2, y is equal to 9, z equal to 0. They generally do not have fluorine present there. So, z always will become equal to 0. So, from there number of carbons will be equal to x plus 1, that is equal to 2 plus 1, that is 3. Number of hydrogen will be equal to y minus 1. So, 9 minus 1, that is 8. Fluorine will be equal to 0. So, chlorine or something else you can easily calculate, actually there is no need to calculate, because as there are 3 carbons, the total number of other molecules or sorry other atoms that can be present is equal to 3 into 2 plus 2, that is 8 only. So, his symbol is C3H8. Which one? What is this? This is nothing but propane. So, C3H8 is propane. Similarly, we can calculate others also. You can easily calculate. I ask you to calculate for a few others, like say the ethane or methane that we have written. You can easily find what can be the corresponding symbol in terms of this convention. The fourth possibility is the mixtures. We shall not be talking about the mixtures, but there generally are two types of mixtures that we consider: azeotropic and zeotropic. Now, for azeotropic one, we write RF, then something else, where this F indicates to the azeotropic. Like for inorganic refrigerants or natural refrigerants, we use that 7 to indicate we are talking about natural refrigerants. Similarly, the 5 indicates that we are talking about azeotropic mixture, and similarly 4 talks about the zeotropic mixtures. And for this to fill up the two blank space, we have to look to some reference tables. So, these are the naming conventions that we commonly follow for refrigerants. Here the this particular one and this one are the most common ones. The first category where we talk about the synthetic refrigerants, which is most commonly used in for both domestic and industrial applications. So, you now know how we give the names this R11, R12 etc., once we have the chemical composition known to us. Similarly, for pure fluids, just like this way, putting the 7 and then the molecular weight, we can also form the symbols for any natural refrigerants and for similarly for any kinds of other refrigerants. So, that is about the refrigerants for which are commonly used for vapor compression based systems. So, now we already have some idea about the vapor compression based systems. Let us talk about a few possible innovations or improvement in the classical vapor compression design, particularly the SSS design. That is a very classical design, and therefore, it has gone through several stages of modifications or improvement over the course of time, mainly to suit different kinds of application. And one big problem that we have is when we have to deal with a very large difference, temperature difference between the evaporator and condenser, because we know that as the condenser temperature increases, the COP decreases. Similarly, as the evaporator temperature decreases, the COP also decreases. Now, the condenser temperature generally is fixed by the atmospheric consideration, but if we are looking to refrigerate something at very low temperatures, that is your evaporator temperature is too low, then if we are looking for just the normal cycle, then your COP will be extremely low, and therefore, we may have to go for several kind of modification, just like this one, the cascade refrigeration system, where not one, but rather we have two refrigeration cycles, quite similar to the combined cycle that we have discussed earlier in conjunction with the power cycles. It is also something like a combined cycle used for refrigeration purposes. Here, just look at the bottom cycle given by this B. This bottom cycle is picking up the heat from the cold refrigerated space. QL amount of it has been picked up in the evaporator, then it has the compressor, the condenser and the expansion valve, but its condenser is not rejecting heat to the surrounding, rather the condenser is rejecting heat to the evaporator of the topping cycle, which is A. So, the topping cycle is not receiving any heat from the refrigerated space, rather it is receiving heat only from the condenser of the bottoming cycle, but it is rejecting QH amount of heat to the warm environment or to the upper atmosphere. So, here this is sorry, this QL is equal to your evaporator load, this QH is equal to your condenser load, and whatever we have in between, this QL does not seem to be correct. Let us strike this one off. So, whatever amount of heat transfer is taking place in this heat exchanger from the condenser of the bottoming cycle to the evaporator of the topping cycle, that is only interior to the system, and therefore, when we shall be calculating the performance of this, we only have to consider this evaporator load and this condenser load, and of course, the compressor work, and here we have two compressors. So, this is a compressor where we are giving say WC amount of WCB amount of work input, and this is the compressor where we are giving WCA amount of work input. So, total work input definitely will corresponds to this two compressor works together. Now, what is the gain that we have here? Just look at the corresponding TS diagram. Here this TS diagram has been drawn assuming both the refrigerants to be same, and that is why you are having the same TS diagram. But it is very much possible that we can use different refrigerants also. In that case, the saturation dome also we have to draw two saturation domes for two refrigerants. Now, if it is the same refrigerant, then look at the bottoming cycle. This is a standard standard diagram for any VCRS, that is 4 to 1 is the evaporation process, then 1 to 2 is the compression process, 2 to 3 is the condensation, and 3 to 4 is the expansion in the valve. Now, how much is the total amount of heat this rejects in the condenser? That total amount of heat rejected will be equal to, or rate of heat rejection in the condenser by the bottoming cycle will be equal to m dot b, that is the mass flow rate, into the change in its enthalpy, which is H2 minus H3, and that is the amount of energy that has been picked up by the topping cycle when it goes to this process from 8 to 5. So, assuming there is no heat leakage, then the total amount of energy picked up by the topping cycle will be equal to m dot A into H5 minus H8, or if we want to get a ratio of these two flow rates, m dot A upon m dot B will be equal to H2 minus H3 by H5 minus H8. So, once we know all the state points, then we can easily calculate the ratio of the mass flow rates. And now, this 5 to 6 is the compression process in the topping cycle, and then we have the rest of the process. 6 to 7 is the process during which heat is finally getting rejected to the surrounding. Now, if we want to reach from this, let us say talk about this temperature to be equal to your evaporator temperature of the combined system, and this corresponds to the saturation temperature corresponding to your final condenser pressure. Then if we want to reach this final condenser pressure from the initial evaporator pressure, then you would have ended up after the compression at this particular point 2 prime, that is 1 to 2 prime would have represented the single stage compression. Rather, what we are having here the compression is being achieved at two steps, and as the temperature at point 5 is lower than the temperature at point 2. So, the work input required for the second stage of compression, that is represented by this process 5 to 6, is definitely much lower than the work that would have been required during the compression 2 to 2 prime, and therefore, the shaded area, the area shaded in pink, that there is a decrease in the total compression work. So, we are gaining from the compression work point of view, and that is the first big advantage. We are having significant reduction in the compression work requirement. Now, how much is the total compression work? Total W dot C will be equal to, or WC will be equal to WC for the A part plus WC for the B part. Now, WC for the A part will be how much, or if we want to write say the total work input requirement, so that will be equal to m dot A into the compression process is H6 minus H5, and similarly for the bottoming cycle m dot B, the compression process corresponds to an enthalpy change of H2 minus H1. So, COP of this combined cycle will be equal to your Q dot E by W dot C. Q dot E is the evaporator load or refrigerator load picked up by the bottoming cycle, which is m dot B into H1 minus H4 divided by m dot A into H6 minus H5 plus m dot B into H2 minus H1, and if we divide everything by m dot B, then this becomes H1 minus H4 divided by m dot A upon m dot B into H6 minus H5 plus H2 minus H1. So, that is the COP of this combined cycle. But there is another thing to look for. There is definitely a decrease in the compression work, but there is also increase in the refrigeration capacity. How that is possible? Instead of this combined cycle or cascaded cycle, if we are using just the single stage cycle, then the state at the end of compression is this point number 7, and as we are following an isenthalpic expansion, so it would have ended up at this particular point, say 4 prime. So, your evaporation process would have started from point 4 prime only, and therefore, this particular shaded area represents the amount of refrigeration load This shaded area represents the amount of refrigeration capacity that we are actually losing or we would have lost. So, as we are going for the cascaded cycle, the state at the beginning of evaporation is 4 instead of 4 prime. So, instead of having the evaporation process going from 4 prime to 1, we are actually going from 4 to 1. So, we are able to put or able to have a much larger amount of cooling load being absorbed in the evaporator. So, this cascaded cycle also giving us an increase in the refrigeration capacity. Therefore, when we are going for a very large change in between the refrigeration and condensation evaporation and condensation temperatures, then use of a cascade refrigeration system gives us advantage in twofold. It reduces the compression work requirement and also it increases the refrigeration capacity, and therefore, this whole thing gives an increase in the overall COP of the cascaded system compared to the equivalent single phase system. Also, it is possible to reach very low evaporator temperatures, as I have mentioned earlier. Each of the cycles has their own COPs, and therefore, each of the cycle, none of the cycles are operating over a very large temperature change, rather the temperature range corresponding to each of the cycles are much smaller compared to an equivalent single phase cycle. So, we can easily go to much lower evaporator temperature level despite getting a reasonably high COP. And also, as I have mentioned, it is very much possible that we can choose two different refrigerants. It is not mandatory to have the same refrigerant. If we are choosing two different refrigerants, then we have to plot two different saturation domes to have the final TS diagram. But it is very much possible, like suppose your bottoming cycle is working within a temperature range of -50 to -10 degree Celsius, whereas the topping cycle is working at -10 degree Celsius to 30 degree Celsius. Now, you may have the refrigerant B which is more suitable for that sub-zero operation, whereas refrigerant A is more suitable for the high temperature range. Therefore, you can easily go for two refrigerants. Like suppose if your topping cycle has the lowest temperature of 5 degree Celsius and a highest temperature of 40 degree Celsius, then you can even use water also as the refrigerant. Whereas, for the bottoming cycle which is going to sub-zero temperature levels, we definitely can't use water because water will become solidified. Let us now take a numerical example just to see how we can deal with this cascaded refrigeration system. And I should mention that here, though we have talked about two stages, but it is possible that we can have more than two cascaded stages also. 3 or 4 stages are also very much possible, particularly when we are looking to go for very low like cryogenic level temperatures. Now, in this problem we are talking about a two stage cascade refrigeration system operating between pressure limits of 0.8 megapascal and 0.14 megapascal with R134 as the working medium. Heat reaction from the lower cycle to the upper cycle takes place in an adiabatic counterflow heat exchanger at an approximate pressure level of 0.32 megapascal. Truly speaking, here we have assumed that the condenser temperature for the bottoming cycle and the evaporator temperature for the topping cycles are same and their pressures are also same, but that is not true in practice, because the condenser temperature has to be slightly higher than the corresponding evaporator temperature, otherwise there will be no heat transfer. So, the condenser for the bottoming cycle will work at a higher pressure level compared to the evaporator of the topping cycle, at least as long as we are going for the same refrigerant. But still here we are approximating the pressures to be same, that is 0.32 megapascal. Now, the mass flow rate for the upper cycle is given. So, we have to determine the mass flow rate in the lower cycle, cooling capacity, net compression work and overall COP. So, this is the TS diagram for the cycle. State points are shown. Once I provide you the refrigeration, once I provide you the property chart for R134A, then you can easily find the properties. Just to show you some examples, say point number 1, we know that point number 1 corresponds to a pressure of 0.14 megapascal and a quality of 1, correspondingly H1 will be equal to Hg at that particular pressure and S1 will be equal to Sg at that particular pressure. So, point 1 is defined. Point 2, the pressure at point 2 will be equal to the intermediate pressure, which is 0.32 megapascal, and we know S2 will be equal to S1 because this is isentropic expansion, nothing is mentioned about isentropic efficiency. So, we can assume that to be 1. So, using this we can easily get the value of H2 also. So, this is the value of H1, this is the value of H2 taken from the tables. What other points we know? Okay, point number 3, we know this is the condenser for the topping cycle. So, here this condenser for the bottoming cycle, rather pressure is 0.32 megapascal and quality is equal to 0. So, you can easily calculate value of H3 and we know H3 is equal to H4. So, we know the value of H4 as well, because 3 to 4 is an isenthalpic process. Similarly, for the topping cycle, for point number 5, we know that pressure of the at this particular point is the intermediate pressure, that is 0.32 megapascal and quality is equal to 0, quality is equal to 1 because this is saturated vapor. So, combining this we can get H5 to be equal to Hg corresponding to P5 and S5 is equal to Sg corresponding to P5. Point number 6, we know P6 is equal to the highest pressure of the cycle, which is 0.8 megapascal and S6 is equal to S5. From there we can get H6. So, this is your H6 and H5 is marked here. Point number 7, that is the end of condensation in the topping cycle. So, here pressure is the highest pressure 0.8 megapascal, but here X7 is equal to 0. So, we know that H7 will be equal to Hf corresponding to this pressure and H7 and H8 are going to be equal to each other because that is also an isenthalpic process. So, we know all the enthalpies and it is also given that m dot A for the topping cycle, the upper cycle is 0.05 kg per second. So, you can easily go for the energy balance. First, let us start with the energy balance for the heat exchanger, so that we can get the mass flow rate in the bottoming cycle. So, amount of energy gained by the topping cycle m dot A will be equal to m dot A into H5 minus H8 and amount of energy lost in the bottoming cycle will be equal to m dot B into H2 minus H3. As we know all the enthalpies and also the mass flow rate for the topping cycle, putting this, your m dot B, I have pre-calculated the number, will be equal to 0.039 kg per second. So, we have the mass flow rate for the bottoming cycle or for the lower cycle. Now, the cooling capacity will be equal to, we have to talk about the evaporator of the lower cycle. So, it is m dot B into H1 minus H4. We know H1, we know H4 and now we have just calculated m dot B. So, from there it will be 7.18 kilowatt. Total compression work input requirement, where we have to consider both the compressors. So, for the topping cycle it is m dot A into H6 minus H5 and for the bottoming cycle m dot B into H2 minus H1. Putting that, it will be coming as 1.61 kilowatt. So, this is the net compression work input requirement, of course, assuming both compression processes to be isentropic. And finally, the COP for this system will be equal to the net evaporation load divided by net compression work input requirement. So, 7.18 upon 1.61, it will be coming something like 4.46. So, this is the final result that we are looking for. So, we can see this is a reasonably high COP that we are talking about. If you remember in the yesterday's class, we have solved the same problem by assuming a single stage cycle, where we assumed one R134A based vapor compression cycle is working between pressure range of 0.8 megapascal and 0.14 megapascal, and accordingly did the calculation, and the COP was 3.97 there. So, we are definitely having an improvement in the COP because of this cascading. Another way of getting the same effectiveness is the use of multi-stage compression refrigeration cycle. Here we are not having cascading, we are not having two different cycles, rather we are having just the same cycle, but we are having two compressors. Just look at how this cycle is operating. We are starting from the I am showing both the schematic representation and also the TS diagram. If we start from the exit of the higher compressor, which is point number 4, from there the entire refrigerant is passing from point 4 to point 5, where during which it is rejecting this heat to the surrounding, which is your QC. Then it is getting expanded not to the evaporator pressure, rather to some intermediate pressure. So, we are having some pressure here PC, here we are having some intermediate evaporator pressure PE, but here at this portion we have some kind of intermediate pressure. So, it is expanded to some intermediate pressure following this expansion valve, and there we have a flush chamber. The purpose of the flush chamber is to separate out the liquid and vapor part. Here the liquid and vapor parts are separated, and X fraction, the vapor, that and 1 minus X fraction, that is liquid, they are separated from each other. The liquid part is now further reduced, further expanded to the lowest pressure, that is the PE, and it picks up the evaporator load, which is your Q dot E, and that gets compressed in the lower level of compression. So, we are giving WC 1 here, and now we have a mixing chamber where this 1 minus X fraction of vapor at state point 2 is mixing with the X fraction of vapor that is coming from the flush chamber with state point 3. And because of this, both are at the same pressure, this lower side compressor compresses the vapor from the PE pressure to this intermediate pressure, and so they mix. Here we have 1 minus X fraction of superheated vapor, whereas we are having X fraction of saturated vapor coming from the flush chamber. They mix with each other here, and then the total quantity of mixture with this intermediate pressure, total quantity of this vapor with this intermediate pressure goes to the higher level of compressor, where it gets compressed up to the final pressure of PC, and we need to get WC 2 amount of work input there. So, look at the TS diagram. Here 1 to 2, here the lower cycle that is drawn, that actually operates over 1 minus X fraction of mass. Here with 1 minus X fraction, energy is being picked up, and it is also compressed, and at the end of compression the state is 2. Similarly, the point 6 is the flush chamber, where we are separating this 1 minus X fraction of liquid and X fraction of vapor. This X fraction of vapor and 1 minus X fraction of superheated vapor, they are mixing and giving this final mixture of point at state point 9, which is getting compressed to final maximum temperature of 0.4. So, how can we calculate the cooling load in this case? Here your Q dot E, you have to remember that we have different mass prevailing during different operations. So, here it will be 1 minus X into total refrigerant flow rate into H1 minus H8, or if we are looking for specific effect, it is 1 minus X into H1 minus H8. And similarly, at point number 9, that is in the mixing chamber, here that is I am talking about, we are having some kind of energy balance going on. How can you write that? The amount of energy coming from the compression side is 1 minus X into m dot, this is the mass, into its enthalpy is H2, plus the one coming from the flush chamber is X into m dot, into it is coming with enthalpy H3. They are giving the final mass m dot, they are mixing with each other to get the final mass m dot and coming with state point H9. So, if you remove m dot from there, it is 1 minus X into H2 plus X into H3 is equal to H9. So, from there we can identify the location of this point 9 if we know 2 and 3. And how much will be the compression work? W dot C for the lower side one, which is W dot C1, and for the higher side one, W dot C2. So, W dot C1 is 1 minus X into m dot into the change in enthalpy is H2 minus H1, and for the higher one it is the total mass that is passing through the higher one. So, it is m dot into change in enthalpy, that is H4 minus H9, or dividing both sides by m dot, the amount of compression work requirement per unit mass flow rate will be equal to 1 minus x into H2 minus H1 plus H4 minus H9. So, it is quite similar to the previous case, but we are not having any heat exchanger, rather we are having a flash chamber where we are having a direct mixing and we have a phase separation. So, the advantage of this multi-stage compression is like a similarly a reduction in the compression work, because had we been using the a single stage compression without any flash chamber, then this point would have been somewhere here. Just by expanding this, we would have got the final point 4 prime maybe somewhere here. So, a significant reduction in the compression work that we are getting from here. Then we are, it is possible to reach very low evaporator temperature. We are also, I have not mentioned, but quite similar to the previous case, we are also having a gain in the evaporator load. And finally, the heat transfer is much improved in the flash chamber, because here we do not need to bother about designing a heat exchanger with very high effectiveness, rather we are just having a direct mixing in the mixing chamber and phase separation in the flash chamber. Here I have a numerical example for such a configuration. It is a very long problem, just read it very carefully, let me go through it quickly. So, here we are working between the same pressure levels 0.8 megapascal and 1.4 megapascal, 0.14 megapascal, and the flash chamber is working at this intermediate pressure of 0.32 megapascal. So, we have to calculate the performance of this. So, the most here the just the way I explained in the previous case, we can identify the point like H1 is saturated vapor, similarly and H2 we can get using the entropy balance. Then 0.7 and 0.5 corresponds to saturated liquid. So, from there we can identify 0.6 and 0.8 also. So, we can get H1 as Hg corresponding to 0.14 MPa. We can and S1 which is Sg corresponding to 0.14 MPa, which is equal to S2. So, from there we are getting H2 by identifying the location of this particular point, and then we have H5 which has to be equal to Hf corresponding to the highest pressure, that is 0.8 megapascal, and that is equal to H6 because that is an expansion process. Similarly, we can get H7 as H5 corresponding to the intermediate pressure of 0.32 megapascal, and that is equal to H8 because that is another isenthalpic process. So, these are the enthalpy values H1, your H2, H5, H7 and H8, and similarly H6. But point 6 is the one that is most important from the flash chamber point of view, because from here we are having a mixture from where we have to separate out the liquid and vapor part. Then we have to identify the quality at this point. Now, H6 can be written as Hf corresponding to this intermediate pressure plus X6 into Hfg corresponding to this intermediate pressure. So, from there we know that X is equal to H6 minus Hf at this intermediate pressure by Hfg at the intermediate pressure. So, if you put the numbers, it will be coming as 0.2049. Now, we have to perform the energy balance across the mixture to get 0.9. So, there we know that 1 minus this X6, because X6 is the fraction that goes to the bottoming cycle, that gets expanded in this second expansion process, then in the evaporation process and this lower stage of compression. So, it is 1 minus X6 into H2 plus X6 into H3, that should be equal to H9. From there we are getting H9 to be equal to 255.1. kilojoule per kg. Similarly, we can also perform an entropy balance 1 minus X6 into S2 plus X6 into S3 is equal to S at 0.9. We have to remember here that we are picking up this point number 3, because once we have separated the liquid and vapor phase, the vapor phase will assume the property of the corresponding saturated vapor and liquid phase will assume the property of the corresponding saturated liquid. So, we are using 0.3 and not enthalpy of 0.3 and not enthalpy of 0.6, and same for entropy. So, similarly, S9 will be coming as 0.9416 kilojoule per kg Kelvin, and we know that S9 will be equal to S4. From there we can identify the value of H4. So, once we know the value of H4, which is shown here, then we can easily do the other calculation, like QE will be equal to 1 minus X6 into H1 minus H8, total compression work W dot C equal to 1 minus X6 into H2 minus H1 for the lower cycle, plus H4 minus H9 for the upper cycle, and once we combine these two, we shall be having a COP of 4.47, which is very similar to the one that we got in the previous problem, where we used an heat exchanger instead of the flash chamber. So, flash chamber is a much easier configuration, much easier to control instead of the heat exchanger, and cheaper as well, and therefore, quite often instead of designing a heat exchanger or going for a cascaded system, we going for a flash chamber based system just like this. We can have a few other designs also, like this is a multi-stage refrigeration system with single compressor. This is something that we have actually in our domestic refrigerators. Remember, in our domestic refrigerators, we are actually in need of refrigeration at two different temperature levels. Like the common foodstuffs, fruits, vegetables that we store in the normal refrigeration compartment, there we do not need to go for very low temperatures. There we generally have lots of moisture content, and therefore, we generally maintain the temperature above 0 degree Celsius to avoid any kind of freezing. But in the freezer compartment or in the chiller, where quite often we store the fish or meat kind of products, perishable products, or maybe ice creams or similar kind of items, there we have to go to much lower temperature. Quite often the temperature may be in the range of minus 15 to minus 18 degrees Celsius. Now, if your freezer is at a temperature of minus 18 degrees Celsius, then the refrigerant needs to be at a temperature of say minus 25 degrees Celsius, whereas in the normal component or normal compartment rather, your refrigerant may be just around 0 degrees Celsius. So, how can we have these two temperature levels using a single compressor? That is what is shown here. Here, after the condensation process, while passing to the expansion valve, we expand to the intermediate pressure level, which gives us the required temperature for the normal refrigerator. And now, once it has picked up the heat from this refrigerator compartment, then it is allowed to expand further to the lowest possible pressure level, so that it can reach the freezer temperature, and finally this thing comes out and goes to the single compressor. So, here the cooling load comprises of two parts. Here your total cooling load Q dot E is the cooling load picked up from the refrigeration compartment plus the cooling load picked up from the freezer compartment, but we have a single compressor which is dealing with the entire mass. Sometimes we may have this alternative path as well, that is here a part of the mixture, or rather a part of the refrigerant, say X fraction, goes to the refrigerator, and remaining 1 minus X fraction is allowed to expand further to be supplied to the freezer compartment, and whatever is supplied to the refrigerator, that comes back via the second expansion valve by this one and mixes at this particular point, just what shown on this TS diagram. And also the advantage of having this alternative path is that we can easily run the refrigerator without running the freezer, or maybe we can run the freezer without running the refrigerator as well. So, we have lots of flexibilities. You must have heard different advertisements where your system has the flexibility of converting the refrigerator to a freezer, or a freezer to a refrigerator, or maybe run the entire system just as a refrigerator. So, this is just by placing this expansion valve suitably and by their suitable combination, that is all. And a final application that I am going to talk about the VCRs is the liquefaction of gases. Now, in several situations we may have to go to extremely low temperatures, like when you want to separate out the oxygen and nitrogen from air just by liquefying them. Under normal atmospheric condition, there is no way we can separate them out, but as their boiling point are separate. So, if we keep on lowering the temperature, then beyond a particular temperature level, or once we go below a particular temperature level, oxygen becomes liquid and thereby gets separated from the gas, whereas nitrogen has a much lower boiling point. So, nitrogen still remains as a gas. In order to separate nitrogen, we have to lower the temperature even further. There can be another application where preparation of liquid propellants for rockets, where we may have to go to extremely low cryogenic level temperatures, study of material property at ultra low temperature, again something related to cryogenics, special phenomena such as superconductivity, which appears only at extremely low temperatures. In these cases, we go for multi-stage compression. We have multi-stage compressor, where by several stages of compression we can move from extremely low pressure levels to significantly high pressure levels as well. And also we have a regenerator as the refrigerant is coming from the heat exchanger, which is nothing but a condenser rejecting heat to the surrounding. When it is coming back, it still is at a higher temperature compared to the returning refrigerant, and therefore it rejects heat to this. Then it there is the expansion valve which takes it to the lowest possible temperature, and from there once it gets condensed, we remove the liquid part. Like if we are talking about the liquid oxygen separation, then this is the liquid oxygen that is separated, and the vapor which has very less amount of oxygen presence, that is recirculated back, and it is being at a lower temperature. So, we heat it up in the regenerator and then it goes through multi-stage compression process. This is a multi-stage compression process shown here. As we are using multi-stage compression, so with proper intercooling we can have this compression being done nearly at constant temperature. Now, here this entire compression process and also the regeneration process is happening when the entire working medium is at the superheated condition, but only during this expansion process from this 5 to 6, it is expanded from some superheated pressure level to some supercritical pressure level to some subcritical pressure level, so that we can have this phase change and we have a mixture formation. Of course, we have to go to very low temperature levels, like if we compare some of the critical temperatures for common gases, like helium has a critical temperature of minus 268 degrees Celsius, and hydrogen has something like minus 240 degrees Celsius. Nitrogen, it is much higher, about minus 147 degrees Celsius. So, we at least to get liquid nitrogen we have to lower the temperature below this minus 147 degrees Celsius, and in single stage of compression that is not possible. We can go for multi-stage compression with regeneration, just like shown here, or we can go for a cascaded system, several stages of cascading, so that we can reach such low temperature levels. So, these are all different varieties of vapor compression based refrigeration system. This particular cycle is known as the Linde-Hampson cycle, the one that I have shown here. So, these are all different varieties of vapor compression based cycle, where we are working with a vapor, and the one that is getting compressed, that is generally a superheated vapor, but during some stages of the cycle we are having phase change going on, liquid to vapor conversion and also vapor to liquid conversion. But it is also possible that we may perform the entire cycle in the above the critical point of the working medium, thereby maintaining the gas phase throughout, and therefore we can also have the gas refrigeration system. I would like to talk very quickly about this. There are gas refrigeration, we have now seen that once we reverse the directions of the arrows in a heat engine, we basically get a reversed heat engine. So, any power cycle, if we reverse the directions, we get a refrigeration cycle. Like the vapor compression refrigeration cycle that we are talking about, it is the reverse version of what? It is the reverse version of the Rankine cycle, nothing else. Just reverse the direction of arrows in a Rankine cycle and you have the triple S cycle. Similarly, all those air standard cycles that we have learned, if we reverse the direction of them, we are going to get a refrigeration cycle. Like the Stirling cycle, reversing that we get the reverse Stirling cycle, which is the Stirling refrigeration cycle, which is gaining improved popularity, but the one that we are going to talk about here is the reverse Brayton cycle, also known as the Bell-Coleman cycle occasionally. This is the cycle, just the Brayton cycle with reversed directions. So, instead of the gas turbine we have the compressor here, and where we had the compressor there we have the turbine, and we have two heat exchangers. Here this QE amount of heat is being picked up from the cold refrigerated space, and QC amount of heat has been rejected to the warm in surrounding. This is the corresponding TS diagram. So, there are two constant pressure lines, two constant pressure processes and two isothermal processes. So, if we want to calculate the performance of this Q dot E will be, or okay, if I write in per unit mass flow rate basis, then specific refrigeration effect will be equal to H 1 minus H 4, specific compression work requirement will be equal to H 2 minus H 1, and specific turbine work output will be equal to H 3 minus H 4. So, net work input given is the difference between the compressor input minus turbine out and the turbine output, that is H 2 minus H 1 minus H 3 minus H 4. So, COP of this cycle is a specific refrigeration effect by specific work input, net work input requirement, which is H 1 minus H 4 by H 2 minus H 1 minus H 3 minus H 4. This is the way we can go for a gas based refrigeration cycle. Of course, in domestic application and even in large scale industrial application, this gas based refrigeration cycle is not very common, but because one problem is that this heat exchangers, it is very difficult to maintain isothermal condition. There will be significant amount of temperature variation, and when there is temperature variation, then there will be lot of more entropy generation, thereby reducing the overall COP of the cycle. But one big advantage of this cycle is that the components are simple and much lightweight. We do not have to go for a bulky evaporator where we have the phase change going on. We are talking about simple gas based compressors and turbines, which are much simple and lightweight components. Thereby, this gas type based refrigeration system is very suitable for aircraft application, just like the one shown here. We have a compressor, we have the heat exchanger, and we have the turbine. And the cold air that is coming out of this, that cold air is circulated through the aircraft compartment to the cockpit, and thereby picking up the heat, and finally it is either rejected to the surrounding or it may come back to the compressor as well. Another very popular application is if we can go for the liquefaction and cryogenic application through the multi-stage compression. If we are not looking to go below the critical temperature of the corresponding refrigerant, then we can easily go for the gas based cycle, something like this, where we have the turbine, we have the compressor, and we have the regenerator also. So, these are quite popular area of application of gas based refrigeration cycle. If you are interested about the gas based refrigeration, you can read the books a bit more. I would like to finish this one by discussing a simple problem. So, here we are talking about an air cooling system for a jet aircraft where air is bled from the engine compressor at 3 bar. Here we are not having a separate compressor, that is the gas turbine compressor which is running your aircraft. From there at 3 bar pressure some air has been taken out, and in a heat exchanger it has been cooled to 105 degrees Celsius. Now, we are expanding this to 0.69 bar in an air turbine having isentropic efficiency of 85%. The air is then delivered to the cockpit and finally leaves the aircraft at 27 degrees Celsius. We want a refrigerating effect of 4 kilowatt. So, this is the cycle. Here isentropic efficiencies are given. So, we have air coming at 3 bar and 105 degrees Celsius and going to the turbine. Then which state point we are talking about? This particular state point. Here your P3 is 3 bar and T3 is 105 degrees Celsius, that is 378 Kelvin, and also isentropic efficiency for the turbine is 0.85. So, you know the pressures at point number 4, the pressure is given in the turbine, it is expanded to a pressure of 0.69 bar. Now, it is air that we are talking about, so we can assume the properties of air such as K equal to 1.4 and specific it to be equal to 1.005 kilojoule per kg Kelvin. So, we can write T4S upon T3 is equal to P4 upon P3 to the power K minus 1 by K. From there, putting the numbers T4S, I have the calculated value with me, your T4s is coming to be 248.4 Kelvin, which is well below the well below the 0 degree Celsius, but because of the isentropic efficiency it will not be able to reach such low temperatures. So, eta T for the turbine is the maximum possible work output, which is T3 minus T4s by actual work output, which is T3 minus T4. Putting this, we are getting T4 to be equal to 267.8 Kelvin. So, just about 5 degree Celsius. So, then how much is your Q dot E? Here it is given as 4 kilowatt, that will be equal to the mass flow rate into Cp into the final temperature with which this air is leaving minus T4, the supply temperature. The final temperature is given as 27 degree Celsius, T4 we have just calculated. From there we can get the m dot to be equal to 0.124 kg per second, and the other values also you can calculate the same way. The mass flow rate we have got, the final temperature at which it is delivered to the cockpit is this T4, this is the mass flow rate, and power delivered by the turbine. So, W dot T will be equal to this mass flow rate into the change in enthalpy, that is Cp into T3 minus T4, which is coming as 13.7 kilowatt. So, 13.7 kilowatt of power is available from this turbine, which can be used for auxiliary uses as well. So, that takes us to the end of today's discussion, where we have talked about the naming convention of the refrigerants, we have talked about different kinds of VCRS system, and finally the gas refrigeration system. So, we have covered the most part of our refrigeration cycles, but there is one very interesting cycle that is still left, which I shall be talking in the next lecture, which is vapor absorption based refrigeration cycles. So, till then you rehearse these lectures, and if you have any query, please write back to me. Thank you.